Hello, physics class, and welcome to this set of notes called Derive the Five. Before we get into deriving the five equations for constant acceleration, I just want to review what we did at the very beginning of this unit. It was a cart, not a wheel, but we let this go down in inclined plane like that, and then we found some graphs. So I'm just going to fill this in. So here we go, and I have the velocity vectors increasing and the acceleration vectors showing about a constant acceleration going down the inclined plane. So we compared a few things. We took a look at a position versus time, and it had a curve that looked like this. And so we had to straighten it by, instead of doing position versus time, we did position versus time squared, and then we got a nice linear graph so that we found the relationship here was, so instead of y equals kx plus b, in this case we had x was equal to some constant multiplied by t squared plus x0. Okay, and then on the next one, maybe I'll shift to green here, on the velocity versus time, right away when we graphed this, we got a straight line. So our graph here would have been our velocity was equal to some k multiplied by t plus v0. And it didn't take too long for me to tell you that that particular constant here, that is acceleration. So we could say that v is equal to at plus v0, or another way we could write it is that this acceleration we learned was the slope. So we often said, hey, acceleration is equal to the rise over the run. So two different ways of expressing this same thing. And when you look at it, really, if I subtract the original velocity from both sides, that's where I get delta v is equal to a. And when I consider how much time might go by, t and delta t can mean the same thing. So you can see how these are actually equivalent if I just divide by each side by delta t. So that was one of my findings. The other one we looked at was velocity versus position, and in this case we got a curve that looked like this. And so when you straightened it, you did v squared versus x, and you got a line that looked like this. So we said v squared was equal to kx. Okay, now when we did some comparison of all these, this slope here and this slope here and this slope here weren't the same. What we found out was the k value for this one was half of the k value which we said was acceleration. So this one was half the acceleration. So another way we could have written that was x was equal to 1/2 the acceleration times time squared plus k0. So if I subtract delta, or the original position from both sides, another way I could say this is the displacement was equal to 1/2 times the acceleration times how much time goes by. So that was one formula that we had. Here's another formula that we had. And this last one, this k down here, was twice as much as the acceleration. So we could say the final velocity was equal to 2 times the acceleration times whatever position we were at. All right, so that's a bit of a review, and really we've been using this equation a lot, but we haven't really been using this first one or this last one at all. And one of the reasons is because there's a bit of a limitation to these models, is that we're starting with a at the origin at x, the original position is equal to 0, and we're also starting at rest, which means that my original velocity is equal to 0. So I wonder if, what happens when we try to expand this to other starting positions and other starting velocities. So my goal in the next few minutes then is to say, can I develop some more mathematical models that involve these 5 different variables. So I'm going to, instead of using the initial position and the current position, I'm going to talk about delta x, my displacement. I'll talk about the original velocity, the final velocity, how much time's gone by, and acceleration. So there's 5 different variables where the initial velocity isn't necessarily equal to 0. So I'm going to have a VT graph here that starts at some velocity and changes. And here's a couple things that we know already that will be useful when we're having this discussion, is that on a VT graph, the acceleration is equal to the slope, which is the same thing as the rise delta V over the run. So in this case, when we're looking at this, this here would be the rise. This change here is delta V, okay, and this change over here, how much time went by, is going to be equal to delta t, where this would be the initial time, the final time. This would be the initial velocity and the final velocity. I should say that in this particular graph, I'm starting at initial velocity and it has a positive acceleration, but all the work we're doing here could be true regardless of whether it's a positive acceleration or a negative acceleration. The other big thing that we learned from a VT graph is that the displacement, delta x, is equal to the area under the line. I'll put a little parentheses around under because sometimes it can be a negative delta x as well. So here's what I'm going to do. We're going to develop some additional mathematical models in addition to this a is equal to delta v over delta t, and we're going to see if we can sort of strengthen these other ones to make them more true for other situations. So the first one I'm going to look at is say, hey, could we solve for delta x by looking at the area under the line? So this is an example where it doesn't necessarily start at rest. So you see V1 isn't necessarily 0. So if I was to think about this area, well, I could say, maybe I'll just talk about the two areas. I could talk about this rectangle area, and then I could talk about this triangle area. And we've already done this in class, haven't we? But what we're going to do is, instead of having actual numbers, we're just going to write in the variables we have. So it's going to be equal to, maybe I'll write it like this, the rectangle area plus this triangle area. And that rectangle area, well, this side of it is delta t, and this side here would be the same thing as V1. So I'll say it's V1 times delta t, okay, plus this triangle area over here. What could that triangle area be? Well, when I look back over here, let me just see something. This area down here is going to be the displacement, because that is also the area under, and this is that triangle area. And you'll notice that that is the same as this over here. So when I have this triangle shape from a object that's accelerating, it's actually 1/2 times a times delta t squared. So this sort of, we're kind of borrowing from that piece. So I'm going to say that that triangle area is equal to 1/2 times a times delta t squared. That is my delta x. So that is one of my formulas. I'm going to get 5 formulas all together because I'm calling this Derive the Five. Just one way to think about this is this part here is the displacement had the object been going the initial velocity the entire period of time. That would be how far it would have gotten. But because it was accelerating, in this case a positive acceleration on my graph, that's how much further it got. Okay, so that would be the first one. The second one, and the first 3 are really variations of figuring out that area under the line. Oh, you know what, maybe I'll go back to blue. So the second one would be delta x is equal to, again, the area under the line. Now, how else could we figure out that area under the line? Well, instead of this small rectangle, we could actually do a subtraction version. So I could say, well, I've got this really big rectangle, which, by the way, would be equivalent to is if it was going at a constant velocity. If it was going at a constant velocity like this the whole time, and its constant velocity was its final velocity, then it would have gone much farther. So then we have to subtract the area of this rectangle here. So I could say this would be equal to, oh, maybe I need my green again here. That would be equal to this large rectangle minus this one here, so that one gets taken away from it like a cutout. Okay, so the area of this large yellow rectangle would be, again, would be delta t on this side, but the height would be v2. So I'm going to say v2 times delta t minus, now that triangle really is the same area as the other triangle. So I'm going to say 1/2 a delta t squared. And that is my second of the 5. So we've got that done already. So let's look at the third one. And I'll erase my drawings again here. So in the third one would be, if I take this halfway point and I draw it here, okay, so tell me, how would this area here, maybe I'll fill it in, how would this area here, this yellow one, compare with that blue one there? I think you'll see that they would actually be the same area again, so that this rectangle that I'm drawing here would actually be, again, another way of finding the same area, because here I'm giving it more, and here I'm taking it away, but it'll balance out. So really what I want to figure out then is, oh, maybe I'll get a different color here, is what would be this point? Well, it's going to be halfway between V1 and V2. So in this case, I can say, well, halfway between how do you find halfway between two numbers? Like if this was, I don't know, if this was 3 and this was 8, maybe that's not such a good one. If that was 3 and this was 7, let's say, what would halfway between it? Well, you might just kind of be able to figure out that it's 5. But if you say 3 plus 7 divided by 2, you add the two together and you divide by 2, you get 5, which is actually a way of talking about the average velocity. In this case, we can do average velocity by adding the 2 and dividing by 2. It's a little bit different than when I cautioned you early about figuring out average velocity by averaging a bunch of velocities together, because it's because this is a nice constant acceleration. It's not spending more time here than it is over there. So because this is a straight line, we can say we're going to use the average velocity. It's going to be equal to, how do you write average velocity? Like this, average velocity multiplied by time. And how do we figure out average velocity in this case? We say V1 plus V2 divided by 2 times delta t, times time. And there's our third one. There, I'll put some check marks. We got them done so far. Now before I go on, I just want you to take a look at the fact that we have these 5 different variables that we're interested in each time. And one way to organize, I'm going to have 5 mathematical models to solve types of questions for constant acceleration. And in each one of these, there's one that's missing. So when I look at this, there's a delta x, there's a v1, there's a v2, there's an a, and there's delta t. So which one's not there? There's no v2 in this formula. So if you're working with stuff and you go, oh, I don't even need to use v2, I don't need to, it's not given, I don't need to find it, then this is probably the equation that you want to use. In the second one, v1 is now v2, so the one I don't have is v1. In the third one, what I don't have is acceleration. So, and maybe I'll move to the next page here. For equation number 4, I'm going to say, well, hey, which one doesn't have delta x? And I'll tell you how to solve this one. What we're going to do is we're going to start, this isn't an area one because, that's what area under the VT line is. So I'm going to say, let's start with our definition of acceleration. A is equal to delta V over delta T. And I'm just going to rearrange this to solve for delta v. So I'm going to say delta v is equal to a times delta t. And then we're pretty well there, except what I want to do is I want to separate this delta v. So delta v is the same thing as the second one minus the first one. And we could stop there, but usually we like to solve for one thing. So I'm going to say if we're going to be solving for final velocity, we could say final velocity is equal to v1 plus a times delta t. And this one just kind of makes sense too. If you're starting with some initial velocity, it's going to be changing some amount. And here's how much it's going to change. For example, if the acceleration is like 2 meters per second every second, and that happens for 3 seconds, it's going to be a change of 6. So it'll be the initial velocity plus this is how much the velocity is going to be changing will give you your new velocity. So that is my equation number 4. Equation number 5 is a little bit of a crazy one. And there's more than one way to derive these, to show these. What I'm going to do is I'm going to start with this over here. I'm going to start with this v squared is equal to 2ax, and that is from when we straighten this graph out. The problem is that this is only v. This has to work with an original velocity of 0. So we're not quite sure what would happen if we added another starting velocity that was higher up. So I'm just going to say, okay, from the graph, we know that v squared is equal to 2ax, and that's when we're starting at rest, when the initial velocity is equal to 0. So what happens if we make a generic one? Well, in this case, I'll say, don't worry about learning how to derive it, but you can see it's not too surprising that we're going to add v1 squared plus 2a. So it almost looks the same, like we just add a initial velocity. So I use v0 if we're on a graph. This is where it hits the axis for original, and here I like to switch between v1 and v2, so it's from the beginning of my time period to the end of the time period. So really you can think about this as being the same as that. But here is my fifth one that does not have a delta t in it. If you would like to know how to derive, if you're just that kind of person, here is my favorite method to derive this equation, is if you start with the previous one we had. So start with this equation number 4. And hint, the way I often think of it is we're going to use equation 4 and we're going to use our first equation, equation number 1. So I'll be numbering these in just a second. So if we start with v2 is equal to v1 plus a delta t, and now what I have to do is, well, this is squared over here, right? So what I'm going to do is I'm going to square both sides. So if I square the left-hand side, I'm going to switch colors here too. If I square the left-hand side, I'll get v2 squared is equal to, well, if this is squared and that's squared, you got to be careful when you square this. This is like when you square a binomial, and then you get a squared plus 2ab plus b squared. So I'm going to get v1 squared plus 2 times these two multiplied together. So I'll get 2 times, how should I write it, a v1 delta t. I don't know, put them in sort of alphabetical order. Is that alphabetical order? A, v, no, maybe a delta t times v. Okay, whatever. These two multiply together times 2 plus this part squared, so I get a squared delta t squared. At this point you might be, oh, I don't even want to know this stuff, this is crazy. But look how close we are. Look how close we are to looking like this. We got v2 squared here, check. We got v1 squared here, and then something sort of similar here. There's like this 2a and this all comes at once. So I'll tell you, you got to know a little bit of math to do this. v1 squared plus, what we're going to do is we're going to factor out a 2a from both of those terms. So when I factor out a 2a from this one, I get a delta t and a v, right? So I'm going to write the v first, v delta t, right? Sounds good? Plus, oh, and this was supposed to be a v1, right? A v1, because that's a v1. Plus, now how do I factor a 2 out of that? Well, it becomes a half. and then I just have an a times delta t squared. Now you might be looking at this and say, hey, this whole thing is like equation number 1 that we just did. If delta x, we just finished proving that this is equal to displacement is equal to delta x. So what I'm going to do is I'm going to replace that whole thing. v2 squared equals v1 squared plus 2a delta x. Woohoo, did it, okay? Or you can just trust me on this. So here are the equations written in a nice neat font here, and I'm going to forever refer to them as this will be equation number 1, this will be equation number 2, this is equation number 3, that's equation number 4, that's equation number 5, and you might want to organize it by what's not in it. This one does not have a V2, this one does not have a V1, this does not have an A, this one does not have a delta X, and this one over here does not have a delta T. So what's not in it? Okay, so we just finished solving a bunch of problems graphically, and what I've given you here is, I know it looks kind of confusing, but it might just make your life a little bit simpler some of the time, are some mathematical ways to do what you've been doing graphically. So thank you very much, and I will see you in class.